Hello, everyone. You are welcome to today's seminar of our Spring 2024 series. So this seminar is usually hosted by the Gallogly College of Engineering, our graduate student community group. And so briefly, before the seminar by Dr. Wang, I'll first give like a brief introduction of our society, our community. Yeah, so for this academic year, we have Roshan and Rachel as our co-chair, and in charge of the publicity, we have Andrew and Avinash. And also we have like some of the graduate students as member of the support group. We have Filani, we have Noreen, we have Roshan, we have Swapnil and Mayang. And our faculty mentor is, Professor Farouk Mistry. And we usually meet every week. And this semester, our meetings are usually at Wednesday by 7:30. And the meetings are not physical, so they're usually held on Zoom. So if you need a link to the meeting, you can contact Rachel or Roshan. And also every semester, we usually set like the time schedule based on availability of all the leadership team also. So we can accommodate your schedule to attend our regular meetings. And to join our to become a GSC member, you just need to be able to scan this QR code, or you go to your Engage page. You just you log in with your OU ID, and then you click on join. And congrats, you're a member of GSC. Also, we have a LinkedIn group where we share a lot of like professional informations. And to be able to join the group, you just need to scan this QR code or send an invite, and the admin of the group will be able to add you to the group. Also, we have a Facebook page where we share a lot of our activities, because the graduate student community, we have a lot of different activity apart from the seminar, where we host international food evening, faculty mix with the student. Yeah, so to be updated about our latest activity, you can join our Facebook page also. And lastly, we have a YouTube page, a YouTube channel. So where we upload each seminar, each recordings of each seminar. So if in case you miss the seminar for the week and you want to catch up on the seminar presentation, so you can go to our GSC-GCOE, and we usually upload it after the seminar. So you can scan the link to have access to the YouTube page. And also for the for the engineering students, we have like different resources that we use. First, one of them is we have the Dave and Susan Betts team room. So this room is available for the GSC member. So in case you want to have like a small meeting, or you want to have lunch, or you want to take a break from your office, you can email us if you want access. You can email Farouk, or you can email Roshan and Rachel. And lastly, before we start the seminar, we'll post the seminar attendance, the link. So please kindly help us sign the attendance list. And today, the title of the presentation would be Evaluation and Improvement of Nonlinear Control Performance of Air Handling Units. And our presenter today will be Dr. Zufan Wang, who is an assistant professor at the Civil and Architectural Engineering at Tennessee State University. And thank you very much. So I would stop sharing my screen now, and to allow Dr. Wang to share, to start the seminar presentation. Thank you.
Yeah, thank you, Rodney. No, thank you, Liren, for the introduction. Yes. Yeah, also thank you for inviting me in this webinar. I'm so excited with this wonderful opportunity to present my work. Oh, so yes, should I? Oh, yes. Yes, so my topic is the evaluation and the improvement of the nonlinear control performance at air handling units. And this work is done during my PhD study under the advisement of Dr. Gang Wang from University of Miami and also Dr. Li Song from the University of Oklahoma. And also, all of these tests done for this topic are on OU campus by Rod Lee, Marvin, and Liu Ren and Junko. Very appreciate all the tests. So right now, we all know that we have the goal of achieving the net zero CO2 emission by 2050. And the electrification is becoming a very promising strategy. And this, as for the supply side, we are trying to generate electricity by using clean energy, such as wind turbine and solar panel. And on the demand side, the buildings, they account for 75% of the all US electricity use. And they become the very promising end users to promote this electrification. And in commercial buildings, HVAC system comprise 50% of the energy consumption. That means we can do a lot of work on the HVAC system to achieve this goal. So in the HVAC systems, they include the supervisory control and the local control. As for the supervisory control, like based on the energy demand patterns of the buildings, the weather conditions, occupancy information, utility pricing fluctuation, and the grid capacities, the supervisory control will dynamically reset the set points for our space temperature, outdoor airflow, duct static pressure, supply air temperature, etc. By using the rule-based control strategy or the optimization-based control strategies. And these set points will be the reference input to the local control loop. And for the local control, they are designed as the single loop feedback control with the PID controller in this control loop. The actuator will be adjusted to achieve this desired set point. And to maximize the energy saving potentials, the local control loops are supposed to be stable and also have very fast and smooth response to the dynamic set point resets. But however, due to the improper control strategies, 25% to 77% energy can be wasted. And also, if we can adapt advanced control strategies, up to 37% of the energy can be saved. So in the HVAC systems, the air handling unit is a component to serve our buildings. And in HVAC unit, in the air handling unit, the return air and the outdoor air will be mixed in the mixing air chamber, and then the chilled water running through the cooling coil will cool down the mixing air, and then the supply fan will deliver the supply air to the space to cool down our space in summer. And the control loops at the air handling unit will include one is the supply fan speed control. For the supply fan speed control, the fan speed will be modulated to maintain the duct static pressure. And another one is a cooling coil valve control. For the cooling coil valve control system, the valve position will be modulated to maintain supply air temperature. So generally, these two control systems are designed as a single loop fixed gain control. And with single loop fixed controls, this type of control strategy is mainly for linear system, which have the linear component with the fixed gain and the time constant. And also the controller is designed as a PI controller with fixed gains. So for this control loop, the components mainly include the actuator, plant, and sensor. And for this control loop, the sensor will measure the control output and compare it with the reference input. Then the controller will convert this error into the actuating signal, and then the actuator will take corresponding actions to maintain the control output at its desired set point. And specifically for the fan speed control systems, we have two operation parameters, the fan speed and the duct static pressure. The reference input is the duct static pressure set point, and the disturbance input is the terminal box damper position. And for the cooling coil valve control, the operation parameters mainly include the chilled water flow rate and the chilled water loop pressure. It refers to as the DP. And for the reference input is the supply air temperature set point, and it has two disturbance input. One is the DP change, another one is the supply air flow rate change. So the control challenges of the control system and air handling units lie in three key points. The one is that the systems are operated under dynamic conditions for energy efficient operation. And another one is that the components are nonlinear. They have variable gains under these dynamic operation conditions. And third one is that the conventional single loop phase gain control cannot compensate these nonlinearities. And as a result, the system will become more aggressive or unstable. So let's say it in detail. These are the 6 parameters to be reset on the might be reset on the different scenarios. And for example, if in the space the people number is reduced from 20 to 10, then we will dynamically reset the outdoor airflow from 300 CFM to 150 CFM. And with this reduced outdoor airflow rate, the mixing air temperature will be changed. Then with the decreased mixing air temperature, then the chilled water flow rate requirement will be reduced. And then this will impact the valve position. And similarly, in the fan speed control loop, the damper position will also impact the fan speed control. So we can see that the system is always operated under dynamic loads from the full load to partial load conditions. And the component gains, for example, for the cooling coil gain, in this figure, it shows the cooling coil gain variation with the chilled water flow rate. We can see as the chilled water flow rate decrease, the cooling coil gain increase, especially on the low chilled water flow rate. The cooling coil gain increased dramatically here. And for the control systems, the system will have an aggressive response with larger gains at this partial load conditions with a very large gain. So we can see that if the controller is designed by assuming that the cooling coil gain will be fixed, but actually the cooling coil gain will increase dramatically. And then we can say that by using this single loop fixed gain control strategy, the system will become oscillatory or even unstable. Here we can see under higher chilled water flow rate condition, the system is stable and smooth, but under lower load conditions with a lower chilled water flow rate, it becomes fluctuating and even become unstable. So to solve these control issues, currently we have some advanced control strategies, such as model predictive control, fuzzy logic control, and neural network control, and even AI-based control strategies. For all these advanced controls, they have some limitations. They are too computationally demanding for the existing hardware, and they are too complicated with more setup times, and also they are hard to understand for control engineers. And then most of the time they will refuse to implement this type of controllers in practice. But alternatively, there are two advanced control strategies, the gain scheduling control and cascade control. They have a simple controller design and configuration, and they can also handle the nonlinearities. So for the gain scheduling control, this figure shows the block diagram of this control strategy. It's designed by inserting one gain scheduling function to compensate this gain variation of the plant by using the scheduling variables. So it can compensate the nonlinearities, but it requires the control-oriented model. That means you have to know the gain variation of the component, such as a plant or actuator. For the cascade control, to design it, we will add a secondary controller and a secondary sensor to create a secondary loop. Then within the secondary loop, it will respond faster to eliminate the inner loop disturbance and also compensate the inner loop nonlinearities. And for this control strategy, we can say that we have to tune two controllers, the secondary controller and the primary controller. The controller tuning is more complicated, and also we need an additional sensor. So here comes the objectives and approach. First, we would like to develop one approach to evaluate the control performance for nonlinear systems to help us identify the control issues. Then to achieve this, we proposed an operation parameter-based distribution approach. And then we want to develop the gain scheduling or cascade control strategies and validate their improvement for the fan speed control and cooling coil valve control. So this is our studied air handling unit. This air handling unit is serving the buildings on OU campus. So here you maybe you can also visit the air handling units there yourself. So this is the outdoor air duct. This is the return air duct. The outdoor air and the return air are mixed in the mixing air chamber here. And then it will go through this cooling coil. This is a cooling coil inside. And here is a control valve to modulate the chilled water flow rate through the cooling coil. And then the cooling air is supplied through this supply fan and delivered to the conditioned space through this supply air duct here. To do the test, we have some test set up with the sensors. So the fan speed we can get it from the VFD, and the supply air temperature sensor. The supply air temperature is obtained from this the temperature sensor here on the supply air duct, and the valve position can be obtained from the control valve, and the water flow rate can be measured using the water flow meter, which is ultrasonic flow meter here. And additionally, we also have other sensors installed in the system, such as a duct static pressure sensor to measure the duct static pressure. and also the airflow meter to measure the supply air flow rate, and the mixing air, the temperature sensor to measure the mixing air temperature, and also the differential pressure sensor to measure the DP here. So after the system setup, our second task is to develop the control-oriented model. This is a very critical steps. To develop the control-oriented models, we have the theoretical approach and also the experimental approach. So according to the theoretical approach, here we have this fan speed control system, the loop with the component of VFD motor and the fan duct. For the VFD motor gain is the speed change over the command change. Normally, this is the fixed value. And for the fan duct component to develop its control-oriented models, we have two relationships. First is that the pressure drop downstream of the duct static pressure sensor is proportional to the supply air squared. And based on the fan load, the supply airflow rate is proportional to the fan speed. And by solving these two equations, we can get that the fan duct gain is proportional to the pressure drop over the fan speed. Actually, when my advisor and we derived this relation, like this equation simultaneously, we shared each other with the result, and we were so excited about this. We saw this is a very simple, simple relationship between the the operation parameters and the system gain. But we are so surprised that why nobody before derived this, and this do inspire us about our control design. So another approach to derive the control-oriented model is through the experiments. To get the control-oriented models, a series of open loops tests were conducted with the step change of VFD frequency commands. So in this figure, this figure shows the step change of the VFD frequency command with the green curve, and the red curve shows the fan speed change. And to get the VFD motor gains, we will use the speed change over the command change based on its definition. And correspondingly, we can also get the time constant of VFD motor, which is the time for fan speed to reach 63% of its final value, which is the definition of the time constant. And similarly, we can also get the fan duct gain by using the measured duct static pressure and the fan speed. Here, this figure shows the comparison between the theoretical model and the experimental model. We can say that they match very well. And also here, for this relationship, it inspire us for our gain scheduling controller design. So with this derived control-oriented models, we it's showing in this table, and based on this, we tune our controller to achieve an overshoot of 20%. And after this all the component gain and time constant, and also the controller gains are fixed for this system. And similarly, we also derived the control-oriented models for cooling coil valve control system. The control valve, for the control valve model, it can be derived by using the valve characteristic curve This curve normally will be provided by the manufacturer, or it can be obtained from the measurements. With this, we derive this valve gain, which is the ratio of the water flow change to the valve position change. And this will be a function of valve position and DP. And for the cooling coils control-oriented models, it's derived mainly based on the energy balance equations between the supply air and the chilled water through the cooling coil. And the coil gain will be the supply air temperature change over the water flow rate change. And it will be a function of the chilled water flow rate. So similarly, we also did experiments to get the control-oriented models. The experiments was done through the open loops test with the step change of the valve command. So here in this figure, it shows the valve control valve curve with the x-axis at the valve position, and the y-axis is the chilled water flow rate over dp square root. Here with this, also you can tell from this valve curve, when the valve position is below 25%, and also when the valve position is beyond 80%, is not very sensitive to the system's water flow rate change. Normally, we will not recommend the control valve being operated under this positions. So we will mainly consider the valve position within the 25% to 80%. And here we did the regression, and we get the relationship of this with the valve position and the chilled water flow rate. So based on this, we can derive the valve gain, which is proportional to the dp square root. And similarly, we also measure the corresponding chilled water flow rate and the supply air temperature, and we calculated the coil gain with the supply air temperature change to the water flow rate change. So this figure shows the comparison between our theoretical model and experimental model for the cooling coil gain. They kind of like for both the experimental and the theoretical model, the cooling coil gain can be approximated as a power function of the chilled water flow rate. And so here we have this relationship, but it kind of like this friction, the power here is very hard for the gain scheduling design. Then we will to simplify this by sacrificing some performance with a simpler format. So this table shows the component gain and time constant. With this, we tune the controller under the design conditions to achieve an overshoot of 20%. And we get our controller gains. So after we derived the control-oriented models, we would like to develop one approach to evaluate the control performance. For a single loop fixed gain control loop, take the fan speed control system as an example. The closed loop transfer function is the ratio of control output over the reference input. And then we can say if the reference input is normally given, if the control output can be predicted with the closed loop transfer function. And for the closed loop transfer function, its performance is mainly determined by the closed loop poles, which are the roots of the equation when denominator is 0. So we can see that all these component gains and time constants will determine the pole location. That means we can use this pole location to indicate the control output. That is, we can use the closed loop poles to predict the control performance. And based on this mechanism, the root locus technique is developed for linear system with fixed component gains. And they will track the pole location with a variable controller gains. It's mainly used to tune the controller. And then the pole locations on the root locus will be used to reflect the performance. Here, the left finger shows the root locus, and we have 2 points on the root locus with different controller gains. Point 2 has a larger controller gain than that of point 1. And the right finger shows the corresponding step response with the closed loop pole at position 1 and at point 1 and point 2. We can see compared to point 1 at point 2, the system has a more aggressive response. That is, with the less negative real parts at point 2, the response will be more aggressive. And if the real part becomes positive, the system will become unstable. So inspired by this conventional root locus technique, we proposed the operation parameter-based root distribution. This is for the nonlinear system with fixed controller gains, but variable component gains that will be impacted by the operation parameters. And then we want to track the pole locations with the operation parameters. So here, if under one operation conditions with the fan speed and duct static pressure, we are able to calculate the gain and time constants based on our control-oriented models. And with these gains and time constants, we are able to calculate the closed loop poles. If we calculate all the closed loop poles on the various operation conditions with the corresponding operation parameters and put it into one finger, then we are able to track the closed loop poles with the operation parameters we defined as the root distribution. So here we developed the steps to sketch these root distributions with develop the control-oriented models. So for the traditional root locus, we only have one variable, that is the controller gains. But for the root distribution, we will have multiple variable parameters because normally we will have more than one variable operation parameters, and the finger will become more than 2-dimensional, 3-dimensional, or 4-dimensional. Like for example, for this fan speed control system, we have 2 variable operation parameters. One is the fan speed, one is the duct static pressure. And correspondingly, the root distribution finger will be a 4-dimensional finger. And to show it clearer, we split it into 2 parts. One just to show the real part of the pole, and another finger just to show the imaginary part. And to make it clearer, we also draw the contour line of the real part and the imaginary part. And for the pole locations, the real parts will have a larger impact on the control performance. So we will put our focus on the real part. We can see correspondingly when the real part, the negative real part becomes smaller, then the system's performance will become more aggressive. And when the real part become positive, then the system will become unstable. So to test develop the root distribution approach, we in the fan speed control system we tested it under 7 operation conditions with a variable fan speed and duct static pressure. Here in the right table are the tested conditions with the condition 1, 2, 3 have the same duct static pressure but different supply airflow rate with different fan speed. And for condition 4 to 7, we keep the supply airflow rate the same, but change the duct static pressure set point. So correspondingly, all the 7 conditions, the real parts of the closed loop poles are marked on this root distribution. So here for condition 1 to condition 3 with a constant duct static pressure, the right finger shows the corresponding pole locations and the left finger shows the test result. We can see under condition 3 with the lower fan speed, and also it has a more aggressive response here. And correspondingly in the root distribution at point 3, the real part, it has a smaller negative real part. So we can see that the performance can be predicted by this root distribution, and also the system will have more aggressive response on the lower fan speed. And similarly, we for conditions 4 to condition 7, we can see the cross from this one under condition 7, the system has the smallest negative real part, and also it shows the most aggressive response. So here we can also see that the more aggressive response will happen under higher duct static pressure. Similarly, we also did the test for the cooling coil valve control systems under 4 test conditions with a variable water flow rate and a DP. So the left finger shows the right table shows the test conditions, and the left finger shows the corresponding real real part of the pole locations. So we can see that under condition 4, we have a less supply air flow rate and with a much lower chilled water flow rate. And also we can notice that the real part become positive here. And here we conducted the test. The right finger shows the test result. You can see like on the condition 4, when the real part become positive, the system is unstable. And here from a test result, the system is unstable here. And also under the condition 2, it also has a relatively smaller negative real part. And under condition 2, the test result shows the oscillation here. And under condition 3, it has the largest negative real part, and it has the most stable performance here. So we can see that the performance can be predicted by the root distribution, and also for the cooling coil valve control system, oscillatory and unstable may happen at lower chilled water flow rate conditions. So here we have the summary. The operation parameter-based route distribution can predict the nonlinear control performance and help us identify unstable ranging and also identify the impact of very multiple operation parameters, such as how the fan speed and duct static pressure change will impact the fan speed control, and how the chilled water flow rate change will impact the cooling coil valve control. And our control issues are that the supply fan speed response will be aggressive, caused by the fan duct gain variation, and also there will the cooling coil valve control system will be oscillatory or unstable, caused by the cooling coil gain variation. To solve these control issues for fan speed control system, we designed the gain scheduling controller. Inspired by the relationship of the fan duct gain and the duct static pressure and the fan speed, we designed the gain scheduling function correspondingly to compensate this gain variation. So this is our designed scheduling function. And with this scheduling function, we can see that under different test conditions, for fixed gain control, the system gain will increase under partial load conditions, but by using the gain scheduling controller, the system's gain can be fixed. That means with the fixed system gain, the system is expected to have identical performance under these variable operation conditions. So to validate this improvement, we did the similar test with the system designed as a fixed gain controller and the gain scheduling controller. Right now, the finger shows here is the system's response using the fixed gain controller on the different operation conditions. And here, this yellow curve shows the system's performance by using the gain scheduling controller. We can see that under condition 3, where the system has the worst response, by using the gain scheduling control, the system performance can be maintained in good performance. And similarly, here for the condition 4 to condition 7, like by using the gain scheduling controller, we can approximately maintain the identical control performance under all these operation conditions. And to quantify it, we calculated the fan speed oscillation range and also the duct static pressure oscillation range. This is the difference between the average maximum value and the average minimum value. We can see that under the worst condition at condition 7, the fan speed oscillation range can be dramatically reduced from 5 to 1 Hz. So we can see that the gain scheduling fan speed control can significantly reduce oscillation range and achieve the desired performance on the dynamic operation conditions. And that's for the tested conditions. To evaluate the system performance under all operation conditions, we simulate it in the route distribution finger. So here we can see this the left finger shows the system with a fixed gain controller, and the right finger shows the system designed using the gain scheduling controller. We can see with the fixed gain controller, the system has a very large unstable ranging, where the real part becomes positive. And by using the gain scheduling controller, the unstable ranging is dramatically narrowed down. And that's for the fan speed control. As for the cooling coil valve control, we also designed the gain scheduling controller to compensate for the cooling coil gain variation. So this is our cooling coil gain variation with the chilled water flow rate. If we want to design the scheduling function to entirely compensate this nonlinearities, the scheduling function will be very complicated, and also this is beyond the system's capacity. And then finally, we design the scheduling function. We simplify the scheduling function to make it simpler. And even though this scheduling function cannot 100% compensate the nonlinearities, it can also dramatically reduce the varying range of the system gains from 23 to 4 times. Here under the from the full load condition to the low load condition. Another approach is to kind of like for the gain scheduling approach, our main purpose is to compensate the cooling coil gain variation. And another approach is to use the cascade control. To design the cascade control, we will add another controller and also the flow meter to create the inner loop. And the cascade controller will be able to reduce the impact of the DP change and also help to compensate the control valve nonlinearities. Kind of like for the gain scheduling is to handle the cooling coil gain variation, and the cascade is to handle the control valve nonlinearities. Then we think of by combining these two, we are able to compensate both the control valve and the cooling coil nonlinearities. And this is the cascade plus gain scheduling control design, with each controller handle the corresponding nonlinearities. So we did the test to to compare the performance of all these different control strategies with a single loop fixed gain control, cascade control, gain scheduling control, and the cascade plus gain scheduling control on the higher load condition and the lower load conditions. So the left finger shows the response under higher load condition, and the right finger shows the result under lower load conditions. We can see here the yellow curve, the orange curve shows the loop response with the single loop fixed gain control, and the green curve shows the cascade control, and the blue curve shows gain scheduling control, and the red curve shows the cascade plus gain scheduling control. Here, if we just we focus on the supply air temperature response, we can see the red curve is very perfect. It's very smooth and fast. And when the orange curve is oscillating, right? But if we look at the control valve, the valve position response, we can notice that the red curve, as for the red curve, it has a very high frequency valve oscillations, right? We don't want that happen. So to quantify the control performance, we calculated the relative ISE value of the supply air temperature. Here we can see by using the cascade plus gain scheduling control, the relative ISE value of supply air temperature is the smallest one, which is the best one. However, it has a very high frequency valve oscillations. So we can see cascade plus gain scheduling control has more stable supply air temperature response, but they have a high frequency valve oscillation. And the gain scheduling control here, we can see it can also improve the supply air temperature response without the high frequency valve oscillations. Then to compromise both, then we prefer the gain scheduling control strategy. And also the gain scheduling control is easier, and also it will not cannot require the secondary controller tuning. So similarly, we simulate the control performance under all operation conditions with the variable chilled water flow rate and the DP. So here, the upper left finger shows the root distribution with a single loop phase gain control. We can see here we have the positive real part, which means the unstable ranging. And also by using the other three advanced control strategies, so we can see the system root core locations are all negative. That means the system's stability can be guaranteed by using either of the control strategies. And the cascade plus gain scheduling control can have the best robustness. So here becomes the conclusions of this research. In this research, we developed this operation parameter-based root distribution approach. And this approach can be applied to nonlinear system with multiple varying operation parameters. And it can help us to evaluate the control performance for nonlinear systems under all operation conditions, and also help us to identify the control issues to guide our controller design. And the gain scheduling fan speed control can maintain desired fan speed control behaviors and achieve approximately identical control performance under all operation conditions. And for the cooling coil valve controls, the cascade plus gain scheduling control has the most stable supply air temperature response. However, it will have a high frequency valve oscillation. And while the gain scheduling control can achieve a compromise between the two. And also compared with some existing advanced control strategies, the gain scheduling control has a low cost with no or just one additional sensors. And also it's very simple to design the controller, and it can be readily implemented without any high requirement of the hardwares. And also it's very generic, and it will be applicable to other air handling units. Yes, and that's for about this research. And also actually we also noted some of the control valve deadbands based on our test results. That might be the reason to cause the high frequency valve oscillations. And also based on this, we have our maybe in the future we can test it in a better control valve. And also we want to test the gain scheduling controller in the pump pipe system.
Okay, yes. Thank you very much, Dr. Wang, for the wonderful presentation. Yeah, it's actually interesting to see how the thought process in how you design controllers. Yeah, because most times, like you see, there is like reconfiguration of a control loop. You don't know why. It's actually nice to see like the thought process involved. And so I would open the floor for if you have any question for Dr. Wang, any comments regarding our presentation also. Rodney.
Hey, I have two questions.
Mm-hmm.
Could you go to the slide where you showed the gain scheduling or the root distribution for your gain scheduling model?
The root distribution or the gain scheduling?
Yeah, I think we just passed it. Or maybe it was the combined.
This one?
Yeah, that one. Yeah.
Yes.
I was wondering if you could explain why on the fixed gain controller, like it becomes more unstable as the duct static pressure increases, like more positive, and it's the reverse, like as duct static pressure decreases on the gain scheduling controller, it gets more unstable.
So as the duct static pressure increase, the system is becoming more unstable. Actually, the fan duct gain is proportional to the ratio of duct static pressure over fan speed. The ratio will impact the system's performance. So that means if the fan speed, the duct static pressure increase, right? Then the system gain will, the fan duct gain will increase. The increased gain will make the system more aggressive.
Okay. Yeah, that makes sense.
Here, yeah, it's not depend just by the here. If you see this fan duct gain is proportional to the ratio of duct static pressure over the fan speed, right? And either change will change the fan duct gain. Like higher duct static pressure will be higher fan duct gain, or lower fan speed will result in the higher fan duct gain, and then will be more aggressive response.
Okay. Thanks.
Okay. Yeah, thank you, Renee.
Yeah. I was just wondering, do you think this will be standard control procedure that gets shipped on like physical units in the near future?
Yes, actually, so we tend to reset the duct static pressure on the lower load conditions, right?
Yeah.
Actually, that will be good because if we reset, we reduce the duct static pressure on the lower load condition, then it will reduce this fan duct gain.
I just meant like, do you think Train or Johnson Controls or somebody is going to start implementing this soon? Because it seems like really good results.
Yes, I do think this controller is very simple, it's generic, and very easy to be implemented.
Thanks, that was all I had.
I was sort of thinking the same thing, but I guess it depends on how easily these can be retrofit to the actual current systems. I think that could be the biggest challenge. Is how do you incorporate these sensors along with these control systems that can move the valve and like control all of these things? And so I think that would be the biggest challenge, is what I'm assuming, is to retrofit it to current systems. Because you could always develop them and then they can come in like next 5 to 10 years or so. But buildings is such weird, right? Because they're so rigid. They have already been constructed for a certain amount of like routing of the air and how the air handling unit is positioned within the building itself. So, but it's great. Like these insights are probably so useful for future buildings, energy efficient buildings. And really, it's been a while I've done control systems, but it was very nice to get back to those concepts as well. Thank you so much, Dr. Wang.
Thank you for the comment. And actually, the one advantage of this gain scheduling controller is that the scheduling variables are duct static pressure and fan speed. Right now, for all the buildings, we already installed the duct static pressure, right, to control the supply fan speed. And also the fan speed can be readily available from the VFD, right? This kind of like these two scheduling variables, so we don't have to install additional sensors. It's already there. And also, if the controller is a programmable sense controller, then we can directly input this scheduling function into the system to implement it. And but for the cooling coil valve control, for that gain scheduling controller, we are using the chilled water flow rate. That means if we want to implement that gain scheduling controller, we need to install an additional water flow meter.
Okay, Zufeng, so I have I know your work very well. So I have a question about your career path, since we have most students here, PhD student, right? So Zufeng actually, after obtaining her PhD from University of Miami, and then directly entered this tenure track assistant professor position. This is an amazing experience given current competitiveness in the academia, and without any postdoc. Without any postdoc experience. So can you share your experience from this transition, and then what you think make you stand out to be so fortunate, having this assistant professor position secured?
Yes, yeah, thank you, Dr. Song, for these questions. And also give me the opportunity to share my experience. And I feel very lucky to have Dr. Wang as my Gang Wang from University of Miami as my advisor. I think the advantage for me to get this position is that I had the teaching experience when I was in my PhD study. My advisor trained me how to teach and on two courses. And from the teaching, I got the opportunity to learn some of the content or knowledge very comprehensively. And also I learned how to explain some points, or helped me to rethink my research, and also helped me to deliver my ideas. And the teaching experience is also one requirement for this the faculty position, and that helped me with the teaching part. And also for the research part, I'm so lucky to have two advisors, right? One is professor, one is Dr. Gang Wang for the theoretical analysis, and another one is Dr. Li Song for the test. So I gained during my PhD study, at the very beginning, I learned how to write the papers by Dr. Gang Wang's guidance, and from the the first paper, he was the lead, and he guided me how to write the papers, and after that he let me try it myself. And we have a very great team with Dr. Wang and Dr. Song. Each time for all the papers, we will discuss together, and we will do the revision and turn it around together. And I can learn a lot from their revisions. This can improve my thinking of doing the research. And I feel that's the experience I have during my PhD study. And also I get this position. One is that I'm lucky they just have this position here, and my research fits very well with their demandings.
Thank you, Zufeng.
Yes, I feel like the most helpful one is the teaching experience when I was in my PhD study.
Thank you, Dr. Wang. So does anyone have any comments for Dr. Wang? Farouk? Andrew? Oh, Andrew, okay.
Yeah,
Andrew, can go ahead.
I wanted to quickly follow up on Dr. Song's question. But then, thank you for the presentation. It was great. It was quite a lot, and but then I found it very interesting and educative. So my follow-up question is, how has it been, the experience? How has the experience been as an assistant professor without the postdoc experience, has it been coping? Like, have you been able to adapt well within the, space of time that you've been there? I know in the assistant professorship position, it's not just the teaching, there is also the writing of grants, publications, and other stuff. And it's actually very competitive. So as your PhD experience also helps with that.
Yes, actually, at the beginning of this assistant professor position, I was struggling. Actually, I'm still struggling now to balance the teaching and the research. As Dr. Mystery just recommended me to focus more on my research. But right now I'm very struggling with my teaching also, and I feel low progress. So my research makes me a little bit nervous about my future career, and I feel but it can for the teaching part. Right now I'm totally get used to it, and for the research part, actually, without any postdoc, and I'm also trying to search any other opportunities to have more collaborations. I went to a lot of conference and talked to a lot of people, and I tried a lot of different opportunities. And this summer, I will go to Georgia Tech to participate in their energy faculty fellow program and collaborate with the professors there on some projects, kind of like in some try to get some opportunities to learn from more successful teams, more exciting projects. And I feel I'm still learning, and it's very challenging, but it's more fruitful. Yeah, you can learn through struggling. Yeah, thank you for your question. Yes. And yeah, and after my kind of like I'm working now, not no longer a student. And I feel the PhD study period is my happiest time to do research. I can just focus on my research. I don't have to worry about like the budget, the project progress, right? Kind of like if the day is becoming dark, oh, my advisor is there. He will get me. I can just focus on my research. That's everything I do every day, like learning and doing the research. But right now, you have a lot of errands to do, and I feel it's very hard to focus or concentrate. So just enjoy your PhD study and focus more on your research.
All right, thanks, and good luck. I'm sure Dr. Song has a lot of experience to also share with you on that. Yeah.
Yeah, you have a very good advisor with Dr. Song. Then your PhD study will also be very, very happy and very fruitful.
Yeah, but don't scare them, Zufeng. It's all manageable.
Yes. You see, I'm very good now. Yes, and you have more freedom with your time. You can you can determine which project you have more freedom on your time.
Okay, thank you, Dr. Wan. I just want to follow up on Andrew's question. Like, how do they, I know like there's usually, for assistant professors, I know there's usually like a review period. So how do they evaluate, the performance of like assistant professorship? Is it by the grants you get? Is it by your publications, or what are the like? What do they check basically?
Yes, they have some tenure criterions, including the teaching, the research, and the surveys. So for the teaching, we will have the kind of like the evaluation, the part, and also you have to develop a new course. And for the research, you have to publish they have the requirement to publish the papers and also get the grant, the money.
Oh.
And also, and for the surveys, kind of like it's in the university for some the general surveys. And the most challenging parts will be in the research and the grant, especially the grant. And I also feel like it's also excited actually. There are, and then during my PhD study, I didn't get many opportunities to write a proposal to apply for any of the grants. And right now, I kind of like whenever several faculties they discuss together, they talk, and then they will come up with some think of new ideas to collaborate on one funding opportunities, and you will kind of like you're always trying to find out think of new ideas and to implement it. And these feel like some of your ideas is achievable, and that's the interesting part of it actually. And each time after you submit one proposal, then you start to expect whether my proposal will be accepted or rejected. And yeah, kind of like you have new hope each time you submit a proposal, like you submit a paper. And sometimes I feel like I will be very stressful if I just focus on the submitted work. Then the better way for me is to start a new work, start a new proposal writing. You don't like kind of for me, it's not put your eggs into one basket like this to calm me a little bit down. Yes, and I feel I'm very lucky, and I got some fundings here, and some new fundings with some exciting ideas, and I'm able to I feel very lucky, and I have some opportunities to travel to some national laboratories and to see more researchers and to find more collaboration opportunities. And last month, I went to PNNL and I met with Jinke, another Dr. Song's PhD student. Okay. Yes, I met with Jinke, and we talked some. And we ate dinner together, and we talked more. Kind of feel that's excited
cool.
to meet a lot of people.
Yeah.